you have done some practice on making compounds. There are two different kinds of compounds you can make, ionic and the covalent, and you can name them. Or at least you have rules for naming them. You're going to practice and you'll be able to name them. But what I want to do is introduce you to, essentially, a chemical story. Okay? And the chemical story starts like this. Once upon a time, just like all great stories start, we had something. And then, happily ever after, this is what happened. And so a chemical story is called a chemical equation. The once upon a time are the things you start with, the things that react, the reactants. The arrow indicates something has gone on, and happily ever after is what is produced, or the products, the final products. And so we're going to tell you what we start with, and we're going to tell you what it becomes, and this is a chemical story. Problem is, I want you to tell a true chemical story. We're at Lee, we should be truthful, and so there are some things we have to consider. Now, when you tell a chemical story, there are a couple of numbers that we need to look at on this chemical equation. And so there is a number that is right here, which is different than this number right there. And so the number that is circled is called a subscript, and the number that is underlined is called a coefficient. The subscript number comes from the fact that when hydrogen reacts, it is a +1, and when oxygen reacts, it's a -2, and I have to do my cross, and I get H2O. The 2 is defined by how the things react together. I can't change that because oxygen only reacts as a -2 and hydrogen only reacts in this way as a +1. That's where those numbers come from. But the coefficient numbers, if I have to, I can change those until I make the story correct. And so this says 2 sodium, and that's the element because it's all by itself, plus 2, what is the name of that? H2O? Water. It is a non-metal in front. The systematic name is dihydrogen monoxide, but no one ever says that. Its common name is water. And what we say that arrow means yields or produces sodium hydroxide, 2 of those, plus a hydrogen, and that's a hydrogen gas. The 2 types of numbers, coefficients and subscripts. Subscripts are based upon how the 2 ions react, and the coefficients we can manipulate until we tell a true chemical story. By changing the subscript, if by chance I just want to change H2O to H2O2, all right, I change the compound from water to peroxide. I can drink water. Can you drink peroxide? You can. Should you? No. By changing the subscript, you change what the compound is, how the atoms are arranged. That you can't just do willy-nilly. But if I put a 2 in front of the water, I just say I have 2 of those waters, or I can have 3 of those waters. And that is something that is allowable as you solve a problem. Now, to make a chemical equation a true statement, there is a principle, and a principle that has become now a law. And in chemistry, this law is called the law of the conservation of mass. And so this law actually was not very intuitive to people who studied chemistry early, or even in the time of alchemy. And this is the reason. Has anybody ever had a real wood burning fireplace in your house? Okay, right? And so I used to have one, and I was the one that had to clean it out. So I am very intimately familiar with this. And so I would walk out and grab a big pile of wood, right? And that wood would be pretty heavy. I'd put it in the fire, and we'd light it up. And it would burn, and it would keep our house warm. But at the end, after it's all burnt and it is all done, what is left inside the fireplace? Ash. And I had to scoop out the ash. Did the ash weigh exactly as much as the logs did? No. Ash weighs a whole lot less. For a long time, that simple reaction, the burning of wood, people believed that in a chemical reaction, mass could be lost because the wood was heavy, the ash was light. And so that was the common sense thing, that reactions lost stuff. But if we do the burning of a log in a modern, systematic way, if I put a log inside a box and I put the air inside the box and I weigh the box with everything at the beginning before the fire began, and then I allow the fire to go and inside the box, the wood burns down all the way to ash. And I let it cool, and then I put the box back on a scale. The box before the fire weighs a certain amount, and the box after the fire, as long as it's completely sealed, weighs exactly the same. Now, what happens to the wood, gets converted into two things: carbon dioxide, which is a gas that you can't see. It also gets converted into water, but really, really hot water in terms of steam, which comes out in a way that you can't see. And so if you trapped all of the products combined with everything that you started with and what actually ends up weighs exactly the same. But in the chimney, what happens to the water and the CO2? It goes up the what? Chimney. It converts from something that I can see into something that I can't see. And so the idea, it took a little bit of time to figure this out, but in a chemical reaction, what you have at the beginning must be there at the end. But for a chemical reaction to happen, the atoms, the way they're combined at the beginning, must change at the end, or you have no chemical reaction. And so if I take a look at this reaction, you would see written on a piece of paper, most likely this: CH4, which is one of those common name methane, plus oxygen will produce CO2 and water. Okay? But for it to be true, this is what it looks like. That black sphere is carbon and the white ones are hydrogens. The oxygens are red, and they're manipulated, or they're bound together in a certain way over here in the reactants. When it gets to the end, the carbon is now bound to 2 oxygens, and there are 2 hydrogens for every 1 oxygen in the waters. But if you count up 1, 2, 3, 4 red oxygens, 1, 2, 3, 4 red oxygens, 1 black carbon, 1 black carbon, and 1, 2, 3, 4 white hydrogens, 1, 2, 3, 4. This is a true chemical story. What this is called is a balanced equation. Everything I start with has to be there at the end. And that's essentially what we have to do when we do describe a chemical story. Because what we're going to do from a chemical equation is we can calculate how much stuff we are supposed to get from how much stuff we start with. But we have to make sure everything is balanced so that calculation comes up correctly. And so, balancing equations is important. Now, balancing equations, what you are going to be given is both the reactants and the products. I'm going to give you both sides of the arrow. I'm going to tell you what you start with and what you end with. Okay? You don't have to predict the products, because I'll tell you that. This is the key. You balance each atom one at a time. Each single atom one at a time. And how you do that is you look at both sides, and you find out which side has more. And you find out the biggest one, and it makes a decision about what you have to do to the smallest one. Try to stay with small numbers. Some equations get into large numbers. Sometimes it helps if you make a table. Balance these last, if you can at all, especially in larger equations. Hydrogen, try to keep second to last. Oxygen, try to keep last. Every so often you do have to use oxygen, but it's in a real simple one. But oxygen's usually, if you use that, that usually takes you down the wrong road. Okay? So if you can keep those at last, try to do that. All right, let me show you how I would go about it. All right, at the top I have a compound that is a covalent compound, and I'm going to add some oxygen to it, and it's going to produce CO2 and water. It is an untrue story at this moment in time because it is not balanced. And so I have 3 atoms, carbon, hydrogen, and oxygen. And so the one I'm going to choose is carbon first. Okay? Now, my first thing is going to do this. I'm going to assume that I have, and I'm just going to articulate it for you. I'm going to assume I have one of these. Chemists are lazy. You don't have to write one, but I'm just doing that to make sure that you know I'm considering I have one of those. All right. If I look at the reactant side, how many carbons do I have? 4, right? On this side, how many do I have? 1. Okay. And so, if I have 4 here, on this side, I should be able to make 4, and I can put a coefficient in front, but what number would I put as a coefficient to make the carbons 4? 4. Okay. At this moment in time, I have balanced 1 atom, just carbon. But that has a consequence, doesn't it? When I put a 4 in front of CO2, what have I increased? The oxygen. Okay, do you see that? All right. Now, I go back and I have 2 more atoms to balance, right? The next one I choose is hydrogen. On the reactant side, how many hydrogens total? 8. On the product side, how many hydrogens total? 2. This is the biggie, right? So this is going to be why I make any decision on this side. What could I put in front of this to make it 8? I could put 4. Okay? Because if I write 4 waters out, I count 2, 4, 6, 8 hydrogens total. I have balanced carbon. I have balanced oxygen. No, sorry, hydrogen. I have to do the oxygen now. All right. On this side, how many oxygens do I have? You have 2. Okay. That seems a little small. Right here, how many oxygens do you have represented just here? This one? 8, right? Okay. How many are represented right here? I have 1, 4, and 8. One of those is right. I have 4 oxygens. Okay. One thing that you can do is there's an understood 1 there. 1 times 4 is how many I have. You could also draw out 4 waters to see it yourself. So I have 4 more there. So I have a total of, on this side, 12. So is there any number I can put here to make it 12? 6. The teacher always puts an easy one. The examples are always easy. Yes? If it is ionic, we have to reduce it. But if it is covalent, I can have 4 and 8. And that's why. Covalents are not reduced. You actually have to tell how many of each there are. All right, so up in the first one, that seemed okay. I'm going to show you what happens when you run into a roadblock, okay? Now, if by chance you like to do stuff in pen, this is not the problem to do in pen, okay? Because I'm going to show you what happens using the same logic, and you're going to get to a point, and then you're going to have to change and try something else. All right, if I look at these two, I'm still going to start off with carbon, and I have 4 of them here. I have 1 of them there. I make the same decision. I'm going to put 4 here because I've got carbons. That seems right. I'm going to go back. I have 8 hydrogens there and only 2 there. 8 is the bigger. So I'm going to put 4. This looks like I've almost solved it. And then I go back and I say, I have 2 oxygens here and another one. That makes 3. That's small. Here I have 8. Here I have 4. There I have 12. Okay, I need 12 on this side. Right here, I started off and I said I had 1 of these. So how many oxygens are right here? 1. So subtract 1. I've already accounted for it. I need 11 more. What number could I put right there to make 11? Yeah, you can put 5, that's 10. You can put 6, that's 12. Okay, let's do this. I put 5.5. 5.5 times 2 is 11. Is that right? No. Can you have half an oxygen? No. So that's a problem. Okay? 2 things you can do at this moment in time. You can erase everything, and that's one thing. Okay, and you start over. All right? You would start over by the first number. I know this is where the pen is not great. The first number I started, I assumed there was 1 of them. So I can't assume there's 1 anymore, so I would try 2. 2 doesn't work, try 3. 3 doesn't work, try 4. 4 doesn't work, try 5. 5 doesn't work, you try 6. If 6 doesn't work, you've done something wrong, probably. Okay? But there's another way I can look at this, all right? I have to have all whole numbers. Can I make this whole by multiplying it by something? What could I multiply this and make it whole? I could actually multiply that by 2, and it would become what? 11. If I multiply that, I got to multiply everything. So that's a 2. That's an 8. And that's an 8. Okay? And so you could either do this. Go back and start over and start with a 2. Now I have 8 carbons. On this side, I would have to do it, let's do it in a different color. I'd have to put an 8 to be 8 carbons. Oh, that's exactly what I had down there. And now, being very, very careful, I have 2 of these molecules. 2 of these molecules, and so I have 16 hydrogens. To get 16 hydrogens, I would put an 8 in front of that one. Oh, that's what I got there. And then if I counted everything up, to be very careful, here I have 8 times 2 oxygens. I have 16 oxygens. That's big. And here I have how many more? 8 more. And now I don't have enough hands and feet, fingers and toes. I'm going to have what? How many? 24. Okay. On this side, I need 24. How many do I have right here, oxygens? 2. How many more do I need? 22. And what could I have put in front of this oxygen to get 22? I could put 11. Okay? Both ways will work. One's is quicker than the other. And so, but if you start putting on, you have to erase and start over and erase and start over and erase and start over, something might be wrong. Okay? And so, balancing equations. All right, one at a time, a single element at a time. Okay? Don't get fancy and do groups. A single element at a single time. Because when you start making shortcuts, you get yourself all messed up. All right, we are going to, on this worksheet, work on the top group, not the bottom group. Not yet. There's one thing I needed to articulate, and I'm going to go ahead and do it now. And that's where you have a compound that has parentheses. And so if I have a compound like this, Mg3PO4 2, the name of that is magnesium phosphate. If I look at that compound, I can articulate I have magnesiums. I have 3 of them. I have phosphates, and because that parenthesis is there, the 2 applies to both of them. So I have 2 phosphates. And then in terms of the oxygen, I would have how many? 8. So that's straightforward. Okay, 3 magnesiums with 3 and a phosphate, and 2 of them. Magnesium changes now. For every one, I have 3, and now I have 3 whole compounds, so I have 9. Okay. For phosphorus, we determined that for every 1, I had 2. I have 3 compounds. Then I have 2 for every 1, and I have 3 of them, so I have 6. Oxygen, for every compound I have 8, but if I have 3 of them, 24. Mathematically, what I did here was 3 times 3 is 9. And this one, 1 times 2 is 2, times 3 is 6. And this one, 4 times 2 is 8, times 3 is 24. So counting up atoms within a compound that has parentheses, you have to distribute that. And I know that's a little bit, you got to just keep track of it. And this may be helpful to pull out your calculator just to make sure you're okay. But you think about what's in one of them, and then you multiply it by how many of them you have with the coefficient. And so some can get complicated like that to tell you how many are there. And so I'm sorry I didn't articulate that. Now, in the notes, I have a very simple, really, really simple, and this is where people complain, you only do simple examples and you give me hard exam questions. This is almost too simple, so that's why I gave you the 2 examples before about balancing. But let's try a couple more. I want you to balance the equation, but can you balance the equation just like that? No. Oh, wait a minute. I taught you how to take a name and make a compound. All right? So I'm just going to combine everything that you know. All right? This is where scratch work somewhere versus what you do can get you in trouble. And so to do these types of compounds or these types of things, I'm going to do some scratch work and say, all right, zinc is the element. It has a +2 charge because that's what it says. Sulfide is S. It's number 16. it will become a -2 because it's in the oxygen group, but I could also look that up. And so a +2 and a -2 all come together, so it comes together and is happy. Okay, plus. All right, on your sheet, pick it up and look for oxide and look for oxygen. Is there anything different when you see oxide and oxygen? Oxide is O by itself with a 2-, a single O with a 2- on top. Oxygen is the element, and it is in a group of elements that are special. What is the heading above those group of elements? Diatomics. There are 7 elements that are found in nature that are together. Hydrogen, number 1. Nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. If you look at nitrogen, oxygen, fluorine, chlorine, bromine, and iodine, the shape makes a 7. There are 7 diatomics, and hydrogen is the oddball out. So every time you see oxygen, that is different than seeing oxide. Oxygen is O2. That's the elemental form, and that's how it's found in nature. Okay, got some other compounds to make, so some more scratch work. Zinc is a +2. Oxygen is a -2. And so if I put those two together, they balance out, so that is great. And then the last one, sulfur dioxide. Oh, di, that's one of those covalents, right? And di means 2, so that meant there was how many sulfurs in this compound? 1. And how many oxygens? 2. All right. All is well. Now, I got to go back and balance. Now, here's a booger. 1 zinc balanced. Great. 1 sulfur balanced. Great. 2 oxygens on this side, right? How many do you have on this side? 3. Booger. There's a 3 on one side, that is odd, and a 2 on the other side, that is even. There is nothing I can put in front of here that would ever make it odd. So what I have to do is, I know this is the bigger side, right? That number's even, yes? That number's odd. Is there any way I can make this oxygen even? I can put a 2 in front of it. The reason why I try to make it even is so I can have even numbers of oxygens over here, because this can only go up by evens. That is why I do that. So now, how many oxygens are in the products? There's a total of 4. Could I make this 4? Yes. By putting a what? A 2. And I'm all done, yes? No. What was the first thing I put on here? What number I wrote first? 2 right here. Did that have a consequence? What did I change? Not only oxygen, zinc. And so, now if I put a 2 here, okay, I got zincs, right? But now I have what? How many S's? 2. Can I do a 2 here? Oh, yeah. But what does that do to me? It moves the oxygen. Oh, my goodness. All right. Did I do everything okay? Yes. Okay, so, oh, my goodness. All right. Let's hold back up and see. Wait a minute. Now how many oxygens do I have right here? 4. How many oxygens do I have here? 2. How many oxygens do I have total? 6. Is there any way I can make oxygen on here 6? Instead of putting a 2, what do I put? A 3. All right, let's check. Oxygen is good, right? How about zinc? 2 here, 2 there. Good. How about sulfurs? 2 there, 2 there, and I'm good. That's not an easy one, right? So now you have an example that wasn't easy. Okay? But it got there. You just have to make sure every time you put a coefficient in front of something, it has consequences. And you have to make sure that consequence didn't or it has to be addressed. All right.
So are you putting the 2 under the ZN?
What is it? I put a 2 in front of the ZNS, and I put a 2 in front of the ZNO. This 2, the green 2, was I was counting oxygens at that moment. So there were 2 oxygens coming from the ZN, and there were 8 oxygens coming from the sulfur dioxide. All right, next one. Because this aluminum is not connected to anything, this is the element aluminum. The next thing is sodium hydroxide. That's a compound. So I have to figure out sodium, if I look on the chart, and when it reacts, it's a +1. And hydroxide is a group, and the group looks like this, and it has a -1. And a +1 and a -1 come together, so I can write sodium hydroxide. All right, this was so complicated, I actually gave you that one. Plus hydrogen. Look up hydrogen on your list. Hydrogen is what kind of special? H2. Most of the time, if you're having problems with balancing equations, it is the fact that a diatomic molecule was not, you didn't put it on there. So you've got to watch out for diatomic molecules. All right. Look over here. I got me 3 oxygens, I got me 3 sodiums, I got some aluminum, and I got some hydrogen. Oh, this one's not going to be nice either. I can see it already. Okay. This is probably where you would have gone, and we're going to run into something. All right. Oxygen last, so I'm start with sodium. Okay. I got 3 here. I can make sodium 3 on this side because I only have 1 by putting a 3. All right. That looks good. It's deceptive, but it looks good. All right. The next thing. I look at aluminum. I've got 1 there and 1 there. That seems okay. All right. I'm happy about that. And now on this side, I have how many hydrogens? 3. What do I put here? You can't put a whole number, right? But could you put some other number? What could you have put there to get 3? 1.5. Okay? All right. That is not true. Okay? It is not true because I can never get 1/2 of a hydrogen. But what can I multiply that by to get it whole? I can multiply it by 2, and I can get 3. But if I multiply that one by 2, I have to multiply every one. So what is understood right here? What number? A 1 times 2 equals 2. Times 2 equals 6. Times 2 equals 2. You can have 2, 6, 2, 3. If you didn't do it that way, if you go back and do it the other way, you originally started with 1 in front of this compound. You would have done this. All right? Don't start with 1, start with 2. That would have been 6 sodiums. To get 6 sodiums, I would put 6 there. This would now give me 6 hydrogens. To get 6 hydrogens, I would put 3. And this 2 tells me I have 2 aluminums. I would have put 2. And here I have 6 oxygens, and 6 oxygens would have been done. So you could go either way. Go back to the first thing, double it, and do it again, and you would have gotten to the same place. So whichever you feel comfortable with. Ammonia, common name, plus oxygen, diatomic, nitrogen monoxide, oh no, plus a common name, water. Okay? Now, as I look at this, I see something. How many hydrogens do I have here? 3. Odd. How many hydrogens do I have here? 2. Even. Odds and evens I can't get. So I take the odd one and I try to make it even. What can I put in front of this to make an even number? A 2. 2 times 3 is 6. I have 6 hydrogens. How can I make this? Put a 3. Oh, booger. Okay. And how many nitrogens? 2 here, right? And so I can put a 2 there. And then the last thing I have to do is look at oxygen. How many oxygens here? 2. And how many there? 3. 2 plus 3 is 5. Booger. Okay. So the first number I actually used was this one. I put a 2 there to try to make it even. Could I put a 3 here and work it? 3 times 3 is what? 9, and that's odd. So what would I try? Not 3, I would try 4. Oh, I'm going to try a different color. I'm going to say, let's try 4 instead, not that. That means I have 12 hydrogens. So what can I put in front of this to make it 12? Not 3, 6. Okay. This 4 means I have how many nitrogens? 4, right? So I'm not going to put 2 there. I'm going to put 4. All right. The last thing I have to do is oxygens, right? How many oxygens are represented right here? Right, this one. 4. Okay. How many oxygens are represented right here? 6. 6 plus 4 is 10. I have to have 10 oxygens on the other side. What do I put there? A 5. Okay. Last example. Phosphorus is the element. I just put P. Iron, the 3 version, and oxide, the -2 version. Now, do you see oxide was different? If I saw oxygen, I write O2. If I write oxide, it's an O with a -2 at the top. I have to do crisscross to get Fe3O2. Yields, I love molecular. I have phosphorus, but I have 4 of them. And I have oxide, but I have 10 of them. Plus iron. Yes?
When you crisscross?
Yep. Oh, I died. Thank you. Yep. let me tell you, that would have really messed up my balancing. Should have let me go, because I would have been all over the place and it would never have balanced. And that would have been a great example, because if you mess up something like that, it will really mess up your balancing. It may never get balanced.
You wrote this thing.
That would really do. Okay. All right, I'm going to edit that out, but 2, 3, there we go. All right. Oh my goodness. I see something that is going to be an issue. Yeah, the 3 and the 10. Okay, what is common between 3 and 10? The closest common denominator is 30. How in the world do I make each side 30? What would I have to put here? A 3 there. And what would I have to put here? A 10. That has a whole bunch of consequences. How many irons do I have here? 20. And then how many phosphoruses do I have here? Okay, at this moment in time, I got to make sure, since they're so big numbers, can I reduce it? I have a 12. I have a 12. I have a 10. I have a 3. And I have a 20. Is there anything that I can divide to make whole numbers between those numbers? Mm-mm. Those are literally the smallest numbers that I could get. And so, you have now seen some complicated ones in terms of balancing equations. All right. In this example, I taught you one more thing that you really need to know, and that is how to use the diatomics. You really need to recognize, if you see the name of any of those diatomics, it must be an H2, an O2, an N2, an F2, a Cl2. If not, you'll do one of two things. It'll be good if it doesn't balance, because that means you got to go back and check something. You'll do a lot of work. Unfortunately, you could possibly balance something and it would be absolutely wrong. And unfortunately, on a multiple choice test, that'll be answer A. Okay? So make sure that you are able to identify and place the diatomics on there. All right? And so, when you look at this, this is kind of like the professor's dream question. It basically makes you do everything. It makes you be able to predict the compound itself, make sure it's on the right side, and then do the balancing. It incorporates a lot of things in these. And so at one moment in time, I was just asking you, just make a compound. And that was easy after you practice. And then I asked you, name the compound. And after lots and lots and lots of practice, it's easy. And then I asked you to balance thing, and I gave you it all, and you just had to do numbers. And now I say, do it all. And the do it all is that bottom list on that worksheet. Okay? And unfortunately, the only thing that will help you do these is actually doing them. But again, use your reference sheet to do that. Now,